So it's my pleasure this morning to introduce Elena Queirolo from Rutgers right now. She's a postdoctoral researcher at the Rutgers in the group of Konstantin Mishaikov. So originally she's from Italy. She traveled a lot. She speaks French, which I believe she learned in Switzerland when she was doing her master at École Polytechnique Fédérale de Lausanne. She was there for a master, and then she moved to the Netherlands to work with our dear co-organizer, Jan Bauer van den Berg. She was there for some years, and after doing her PhD, she moved to Rutgers, and her PhD was on validated numerics of periodic orbits, Hopf bifurcations, and continuations, and she developed a kind of a general piece of code to handle a class of ODEs for which she could study bifurcations. And today she's going to talk about an extension of that work, and she moved toward PDEs, and she will talk about applying these techniques to the Kuramoto-Sivashinsky PDE. Please, Elena.
Thanks a lot for the incredible introduction. Thanks a lot for having me here to talk. And I am very excited because I want to present you this relatively old results that I got last year on the Hopf bifurcation in Kuramoto-Sivashinsky PDE. And while I was getting ready to present this talk, I thought that, well, I could actually do some more with the code at hand, and I decided to spend the night on it and have some new results this morning to present to you. So I have some extra degree of excitement this morning given by the very last pictures that I will show you at the end. So this is a joint work with my PhD advisor, Jan Bauer. And now I'm trying to look at a second. Okay. And I'd like to present you a two-step plan to solve math. You first define the problem, and then you solve the problem. And this will be the outline of our talk. So I'll spend quite some time in defining a system of equations that, once we can solve it, would prove the existence of a Hopf bifurcation. And then towards the end of the talk, I will go on the details of looking at the Kuramoto-Sivashinsky PDE in practice and try to validate it. So let's look at a Hopf bifurcation. I think this is a picture that you have seen relatively often. You are looking at a fixed point of a dynamical system that undergoes a bifurcation at a certain point, and at that point it switches in stability, and a periodic orbit appears around the fixed point that we're looking at. And when you're looking at periodic solutions, then the Hopf bifurcation is where your periodic solution gets smaller and smaller and disappears. So if our focus is to look at periodic solutions, then we have the problem that the Hopf bifurcation is where things become too small to study until they get singular. So we would like to find some ways of thinking about the Hopf bifurcation that are compatible with studying periodic solutions that are not singular at any point. So let's try to do this. And this is another representation of the same thing. We have just sliced things up, and we have identified a lambda star in which there is the fixed point that is in green and a periodic orbit that is the fixed point itself. So this is the problem when studying Hopf bifurcations with a look at the periodic orbit. The periodic orbit corresponds to the point you're looking at, to the fixed point. So that can be problematic. So let's try to look at the periodic orbit in a different way. Let's first think about it as the difference between the periodic orbit and the fixed point. So you're shifting your problem around zero, but that doesn't solve the thing that your periodic orbit is tending to zero. So the next thing we can do is trying to rescale it with respect to the norm of the periodic orbit around zero itself, whatever that means. But when we're dealing with smooth systems, adding a norm that is discontinuous, like with derivatives discontinuous at zero, it's not that nice. So instead of adding the norm itself, we're gonna call it A, and we're saying that it's the amplitude of the periodic orbit. A is a value that when A is positive corresponds to the norm, And when A is negative, it's minus the norm. But it allows us some little bit of more flexibility in actually choosing A. So let's think a bit about what A means. When A is positive, then we have a periodic orbit, Z, that is the rescaled version of the periodic orbit of our system. And there is a very simple correspondence to the periodic orbit of the system itself that we will denote Y as a Y that is orbiting around our fixed point. Where A is equal to 0, we have our periodic orbit Z that is rescaled, that is still non-zero because that was the goal that we wanted to achieve, while its corresponding in the dynamical system that we are studying is of amplitude 0, so it does correspond with the fixed point we were looking at. And when A is negative, well, Z, that is the rescaled orbit, is still of dimension 1, but somehow there has been a shift with respect to Y. So if we look at a couple of points, we can see that like a point at the upper right corner has been shifted to a point at the bottom left corner in the orbit Y by the multiplication with A. But if we take 2 points, we notice that the direction of the orbit is still the same. So what is happening is just that we have shifted the orbit by half the period. And that might seem like a problem, but at the center, when A equal to 0, by information on the Hopf bifurcation, we know that Z is a perfect circle. So what is happening is that it's going to be deforming away from 0, and it's going to be deforming in opposite ways in the two sides of A. So we can actually build a symmetry between a tuple AZ and minus AZ, where we just shifted the time in the Z component. With this approach, we went from looking at a dynamical system in Y, depending on a parameter lambda, where Y is a periodic orbit, to looking at three unknowns. X being the fixed point, A being the amplitude, and Z being the rescaled periodic orbit. But the rescaled periodic orbit only exists after we have undergone the Hopf bifurcation. There is no rescaled periodic orbit before that. So when we are looking at it, we can think of the fact that if you're following the periodic orbit Z, then it's going to go from on the right side of the Hopf bifurcation, if that's the side where we have the periodic orbit, towards the Hopf bifurcation and then away from it. And it is touching the minimum value of lambda exactly at the amplitude 0. So this is a general picture that we would like to see when we're studying the A lambda plane, when we're looking at our solution in the expanded system. When we look at the formal definition of Hopf bifurcations, we are usually looking at something that relates to the eigenvalues of the derivative with respect to x to the right-hand side of our ODE. So we say that an ODE is undergoing a Hopf bifurcation at a specific value of a parameter if our derivative of f has a couple of imaginary eigenvalues at lambda star, pure imaginary, that are crossing the imaginary axis with non-zero velocity with respect to lambda. The information about non-zero velocity with respect to lambda is a restriction to require the Hopf bifurcation to be non-degenerate. So at the beginning, we had this really nice parabola coming up from the Hopf bifurcation. If we are not imposing the non-zero velocity, what we could have is a sort of a cusp happening up. And so it's a degenerate Hopf bifurcation because our orbit doesn't nicely grow out from the bifurcation point. How does that relate to our new system in A and Z? What we ask is that the blow-it-off system undergoes a saddle node bifurcation at A equal to 0. What it means, if we go back to the previous view is that when we're approaching a equal to 0 and lambda star, we don't just stop at a equal to 0 and then move again. We smoothly go through that value. So we have a nice smooth curve in there that is square root of lambda with respect to if you're in this plot. Another equivalency that we will be using in the PDE case is that the blow it up system, a prime is different than 0 at a equal to 0. This still means that we're crossing the a equal to 0 bound with a certain speed vertically. We're not stopping there at any point. There is just one moment in which our amplitude is equal to 0. This returns to the idea.
What are you differentiating with respect to which variable are you differentiating when you say prime is not 0?
Something that I wanted to sweep under the rug. The arch length, the arch length of the solution branch.
Arc length. Okay, I see.
So it's again an idea of avoiding the fact that you have a cusp at this point. You really want it to be a vertical in this, a vertical branch in this plane, lambda A. But I was trying to avoid actually introducing the arch length parameter and explaining what the derivative was actually there. Thanks for the question. So now we have drawn an equivalency with the formal definition of the Hopf bifurcation that we're usually looking at to something that in our blow it up system is quite easy to test. We're just checking that A is constantly changing and that is crossing 0. This is something that we're going to be able to do in the PDE form. But let's look at the form of the equations that we have structured when we're looking at an ODE system. So we have a derivative of y being f of lambda y. The parameter has disappeared on the slide, but it's still there. And we are splitting this equation into 3 new equations. One being an equation with fixed point. So we're just requiring that at x, our right-hand side is equal to 0. The last one is the amplitude, so we're requiring that the size of the perturbation be rescaled to 1, such that it never disappears. And the center one is the one we're going to be devoting a little bit more time, because it's the perturbation, and we define it as the difference between the periodic orbit and the fixed point divided by a value a, that we are assuming to be this amplitude that is roughly the norm, but with a sign in front. So let's look a little bit longer at how we can define the perturbation. Well, because of how we are looking at it, we can take the derivative of both sides. The derivative of x trivially disappears because that's what we have imposed when we're looking at the fixed point. So we're left with the derivative of y on the right-hand side divided by a. And at first glance, we're not very happy with that because a is supposed to be going to 0, and it might be a big problem to divide by 0. But I was claiming that this was a system that is sturdier to look at when you're looking at Hopf bifurcations. So I should justify why dividing by a is not a big deal in this context. So let's replace y with the new variables that we have introduced in our new expanded system. And let's do a Taylor expansion on this right-hand side. So we take AZ as the perturbation, and we follow the Taylor expansion through it. And we remember that f of x is equal to 0 because we just set it like that. And what happens is now that all the terms of the Taylor expansion have explicitly an a in front. So we have az f prime plus a squared z squared divided by 2f second, and so forth. We do like finite things, so we are expecting this Taylor expansion to not be infinite. but this is just a practical thing because we want to be computing it later. So we like looking at polynomial problems because these allow our Taylor expansion to be finite and us to look at it in a simple way. But this can be a general approach. So now that A is just everywhere on the top of our fraction, we can just simplify it away. And this is the new equations that we will be looking at. An equation for the fixed point, a scalar equation to rescale the norm of the perturbation that we have introduced, and an ODE for the perturbation itself. Let's look at how this applies to the Kuramoto-Sivashinsky equation. So this is a PDE, it's fourth order. We are imposing periodic boundary conditions on the space variable, and we're looking at just one-dimensional space. And we are going to be using Fourier sequences because we're imposing space periodicity and we're expecting time periodicity because we're looking at a Hopf bifurcation. And if that wouldn't be satisfied, it would be a problem. So we are looking at something that is periodic both in time and in space. So we can use Fourier. And we are applying this approach of blowing up the system. So going from the initial problem in U to a problem in which Y is a stationary solution and AZ is a perturbation in which Z is of amplitude 1. That means that its norm or something similar to the norm is equal to 1. And A is how big of a perturbation you're having in this moment in the Hopf bifurcation. And as a brief overview of how Fourier works in this context, we're having two variables that are in Fourier, Y and Z. Y is something that only depends on the space. So it's a one-dimensional Fourier sequence that we will denote as YK, while Z depends both on time and on space and is a two-dimensional Fourier sequence, but infinite by infinite in both of the two indices. I'm not going to be talking about which norms we're going to be applying here, but we are just going to be applying a norm that imposes the amplitude of our Fourier coefficients to be decreasing the further away we are from the index 0. So we are expecting to have the first elements of the Fourier sequence, that is the ones around 0 as index, to be important for our system, and the further away we are going from index 0, the less important they are. We are interested in doing approximations, so this is something we are really interested in because otherwise we wouldn't be able to truncate our Fourier sequence in a reasonable way. And we can easily move from a one-dimensional Fourier series to two-dimensional Fourier sequences just by saying that there is an embedding in the space variable and 0 everywhere else. So we have this way of looking at Y as also a two-dimensional Fourier sequence if need be. This means that, for example, we can define convolutions between the two elements without that being problematic. And one of the things by which Fourier sequences are really nice is that taking derivatives is extremely easy. So the derivative over time is just a multiplication by the imaginary number and the time index of your element, and the derivative over space is the multiplication of each element by their space related index and the imaginary number. That's valid for Z, that is two-dimensional, but is valid for Y, that is one-dimensional in the same way. Trivially, the derivative over time of Y is equal to 0 because it's something that doesn't depend on time. So applying all of this, and with the operators that we have introduced, we can transform our Kuramoto-Sivashinsky equation into three equations, one being the scalar equation on the amplitude of Z, and two being equations one on y only and the other on z and y, in which we have applied the idea we presented before of doing a Taylor expansion around y plus az and taking away the first equation that is imposed to be 0. So we have the linear terms that are in the first line lambda 2 k4 minus k squared, and in the second line something very similar, but with the addition of also the time derivative, and some nonlinear terms that are of order 2 in y in the first equation and in z in the second. So it's fairly tame as a system because it doesn't have very high nonlinear orders. But the thing we are the most interested in when we're going to be looking at validating such a thing is that our nonlinearity has a lower order in k than our linear term. That will be the one thing we really have to be using thoroughly when we're doing the validation. This guarantees that when we are away from the indices in the Fourier space that we're interested in, so away from 0, the linear term is the one that is the most important, while the nonlinear term can be ignored. And we'll be a bit more precise about what it means later. In here, I did a rescaling in time. So lambda 1 is a rescaling in time such that we are now set in a 0 to 2 pi time periodic situation. And I called gamma, I called it lambda 2 such that our two variables, so lambda 1 and lambda 2. And now that I have explained how we can go from the Kuramoto-Sivashinsky equation to the Taylor expanded blowed up system, I'm just gonna hide it all in a F1, F2 problem that we're gonna set equal to 0. And we're still gonna be taking care of some phase conditions to avoid time shift and space shift and have unique solutions. But that's not very exciting, so I'm not going to be talking about it. But I will be talking about the continuation equation. So we are interested in validating a branch of solutions, and we're interested in knowing that it's passing a equal to 0 with non-zero velocity in a. And the easiest way to do that is just imposing that a is taking a certain value and that value is changing constantly along the branch. And this is what we're doing. So the continuation equation is a parameter continuation in a in which we have complete control of the values a is taking. So if we can solve this problem and if we can prove that there exists an exact solution of this problem, then trivially a prime is constantly different than 0 because we are requiring it to change constantly. So with our equivalence that we have constructed it before, if we can find a solution to this problem, then the non-blowed up system is undergoing a Hopf bifurcation. So we place all of this together and we call it our HS is a problem. It's depending on S, where S is the parameter that defines where we are in the A-related branch. We have some phase conditions, the F1 and F2 problems that come from the blowed up system of the Kuramoto-Sivashinsky, and we're solving for a lot of variables. We are solving for lambda 1 being the time rescaling, lambda 2 being the parameter that we started with, A being the amplitude of our perturbation, y being the stationary solution, and z being the periodic solution around that through the rescaling would be around our stationary solution. And we're going to using the Radii polynomial approach. I'm going to go extremely fast because I'm honestly pretty convinced everybody knows this, but maybe there is one person that doesn't, and they're still going to be introducing the definition. So we're looking at a problem at a very general and abstract setup. We're looking at a problem that is f of x equal to 0, but we're solving it in an approximate way. So we only have x hat such that f of x hat is roughly equal to 0. And we want to find a proof that says that there exists a solution such that the bound between our approximate solution and our exact solution is smaller than some known epsilon. So we expect f to go from between two Banach spaces, and we want to construct a contraction that goes from H to itself. We would like to use the Newton map because we know how well it works near a fixed point of the Newton map, that is near a 0 of the f problem. But computing the inverse of f at any x is usually way more than we want to do. So we want to approximate that with the inverse at x hat. And usually that is even out of our interest. So we're going to approximate it even further by some a that should be reasonably close to our inverse. And if a is invertible, then f of x equal to 0 is in direct correspondence with t of x equal to x. And if t is a contraction, then it has a unique fixed point in the neighborhood. And we can check that t is a contraction on a certain pole if it satisfies some inequalities. So that if y plus zr is smaller than r, where y is the defect at the numerical solution that we have found, and z is a bound on the derivative in the pole that we're looking at. With the idea that the minimal bound gives you the closest place you can find an exact solution to your problem, and you have a maximal radius of uniqueness of that solution. When we're looking into continuation, then we will have our approximate inverse depending on some parameter s. We have two numerical solutions, x0 and x1, and we want to validate the segment connecting them. That means we are expecting a tube around that segment to contain the branch of solutions that we're looking at. And if we're careful enough, we also have smoothness between consecutive segments. The Radii polynomial doesn't change at all, except that now we have maximums over S all over the place. So let's look at a simple application of all the setup that I have been producing. The general setup about blowing up a dynamical system with respect to a fixed point and a perturbation can be applied in ODEs as well, even though I will concentrate a lot on PDEs. So this is a Lorentz ID4 system. It's just a 4-dimensional system with a lot of parameters. We're fixing most of them. We're keeping only lambda being the parameter we're interested in. And we're looking at half bifurcations in this setting. And we could find multiple half bifurcations, for example, a lambda roughly equal to 0.05. And you can see how the green solution is a sine cosine function. And we can continue it away from lambda equal not 0.5 until minus 0.02, where the blue function that you can see is very obviously not a circle anymore. And then we had we can do that in other situations. So we have found 3 half bifurcations in this system. And one had this very weird situation in which we started at the right-hand side on where the parameter mu was slightly bigger than 0.01. And if we followed that branch forwardly, we had a situation in which the amplitude was tending back to 0. So we studied this situation a bit more, and what we could prove is the existence of a periodic orbit, a branch of periodic orbit in a sort of balloon. It starts from a half bifurcation, it walks away from the half bifurcation, and then it starts contracting again towards another half bifurcation. So what we had to do here is some sort of validated gluing of two validations, actually 3 validations. We went from Hopf bifurcation validation to standard continuation, and from standard continuation back to a new blowed up system in the other side of the balloon. The two cyan light blue lines that you're seeing are the lines of the fixed point next to the Hopf bifurcation. They're the only part that hasn't been validated explicitly, but you can see how this balloon is connecting two things, two branches of fixed points that don't interconnect. So there are actually like separated branches, and this periodic orbit is going from one to the other. So let's go back to the Kuramoto-Sivashinsky equation. We did our work in setting up F1 and F2, taking care of our stationary solution and our perturbation. We have added a continuation equation in this bigger HS problem that we're setting equal to 0. We're solving for a lot of parameters. And we're looking at the shape of the derivative at a numerical solution. So we have a couple of equations that are scalar and that only depend on a finite number of nodes. So this are the first elements. Then we have derivatives with respect to scalar elements. Those are the first columns. And here we are definitely missing a, let's go to the next slide because the previous one was wrong. And then we have 3 blocks in which we have the 4 center blocks are infinite dimensional in both directions. And we're having non-zero elements only on a strip along the diagonal. And in this slide, I'd like to have a sort of a heat map of where the most important information is condensed. And it's condensed around the center of our matrix when we're looking at a finite number of nodes, because there is where our the Fourier modes are biggest. But also we have a diagonal that is given by our linear terms. This is where it's important that the nonlinear terms have a lower order in K than the linear terms, because the linear terms are only on the diagonal in our center operator, while the nonlinear terms are spread all over the place. But after a while, the nonlinear terms are definitely way more important than the nonlinear ones. So we have these diagonals that are catching our interest, while the rest is relatively tame around. So when we're looking at this, we can consider making an approximation that is just a couple of blocks wherever the most important elements are, and a tail that we know analytically because that's just the tail of the linear term. This is handy because now we have a part that our computer can handle, that is the blue boxes, and a part that we can handle by hand, that are our 2 diagonals. And that means that when we're computing the inverse of all this, we can just ask the computer to take care of inverting the blue matrix, while we by hand know how the tail is going to handle things. And when we're looking at how this operator acts on other operators, we are always going to be splitting it between the part that the computer can handle on its own, and it's just a big matrix and it's finite, and the part that we have to work with in order to bound everything by hand. So when we're bounding things by hand, we're interested in bounding polynomials over the diagonals that we have computed. And because of the fact that the linear part is the part with highest orders in K, when we are looking at polynomials, those polynomials we're looking at will have order at most equal to our denominator. So we are hoping to do a good job in bounding it. We're also bounding it away from the finite part. So the fact that for K equal to 0, these fractions are ill-defined is not a problem, because we're always keeping relatively big j's and k's. So we can apply some algorithm that can just bound our tails. And as long as we can find a way to bound these tails on a finite number of computations, these are very cheap computations because they're just polynomials over known polynomials. So even if it takes 3,000 iterations to check how to bound these things, that is not our biggest concern. And we can bound this as long as the polynomial p in this setting is of polynomial order at most 4, and that is the case. Again, going back to the idea that the nonlinearity is kept in check by the linear term. So let's go to our validated results. These are the validated results as close as possible to the Hopf bifurcation in the Kuramoto-Sivashinsky equation. We have here plotted the stationary solution. We can bound where the Hopf bifurcation is happening with an accuracy of 3 times 10 to the minus 12. So I'm quite happy with that. And we can construct, and we can also look at the shape of the perturbation near the Hopf bifurcation with the same bound on how precise our approximation of the perturbation is. So, and because we have this continuation array, well, we can just continue it away from the Hopf bifurcation, and we can see how if we take 100 iterations, we can walk away from the Hopf bifurcation, and we start having some minor changes. It's true that 100 iterations are not a lot, but the code is quite heavy, so each iteration takes, on a pretty new computer, some 10 minutes. I couldn't make more runs before this talk. So the first column, you can see the stationary solution and the time and space periodic solution, the perturbation at, so to say, the Hopf bifurcation. In a sense, it is a numerical approximation of where the Hopf bifurcation is. And then we can continue away from it. 100 iterations later, it looks exactly the same. But if we look at the norm of the difference between the two, we actually notice that it is different. We have been walking away from it. So it's the stationary solution changed by 10 to the minus 10, while the periodic solution actually had a difference of 10 to the minus 4. And if you remember before, we had the picture of lambda versus a, so our parameter with respect to the amplitude. And if we're plotting this same picture with this new, numerical results, validated numerical results, we're retrieving the thing we're expecting. That is something that looks like the square root of lambda away from the lambda star. And you might not notice, but the very first dot close to A0 and the smallest value of lambda, it's indeed has a negative. So we are crossing the A equals 0 line, and we are validating the Hopf bifurcation. And I hope I did right, because one of the things I forgot to do is getting a clock, so I have no idea what time it is. So thanks for listening. I hope you enjoyed this talk, and I hope it's not too late nor too early.
Thank you. Can you wait a second? Yes, well, yes, we do have a lot of questions, time for questions. So thank you, Elena, very much. Are there any questions or comments?
I had not so much a question, but just a comment. When you did the example with the Lorentz 84 and you found that balloon structure there with the continuation. Yeah, so that reminded me of something about a couple of years ago. I was reading this paper in a context with mathematical biology. It was by Victor Leblanc u Ottawa, and he was studying these what he called endemic bubbles. And the structure is it's basically this: you have like two Hopf bifurcations that then connect two orbits together, and they fuse. And it actually comes from this. It actually comes from if you sort of, you know, think of it as like what exactly is the bifurcation structure that gives you that, it's actually coming from a degenerate Hopf bifurcation. So there's like ways to like shift parameters around that then can cause that bubble to sort of blow out if you perturb them the right way. So I suppose what I'm saying is, yeah, this structure is there. This structure has come up I've seen it come up a couple of times. So this might be, for example, a good way to actually prove that those bubbles happen. And also, I wonder if there's maybe a way to look at what you've done here to actually look at that bifurcation structure, where exactly that bubble comes from, if you can actually, in some sense, unfold that bifurcation rigorously. I don't know. That's just something it made me think of. It's very cool.
So something like checking both Hopf bifurcations at the same time?
Yeah, I mean, I can't remember the details, but it's some sort of this structure here comes from a codimension to like degenerate Hopf bifurcation, and there's a violation of a crossing condition. I can dig up the paper and look at it later. But yeah, there's something there.
Okay, I would be interested. Thanks for that.
Yeah, no problem. I'll send it to you later. Yeah.
This was definitely an unexpected finding while trying to look at normal Hopf bifurcations.
Yeah, for sure.
So we were quite surprised to find it. But if it's actually unknown information, that would be really interesting. Thank you.
Yeah. Okay. Yeah, you're welcome.
Okay, thank you, Kevin, for the question. Comments? Are there other questions or comments?
Maybe I have a little technical comment. So when you solve this problem of a being the denominator of f of x plus a times z, you solve that problem by Taylor expansion. But of course, in many nonlinearities, f, for example, exponential or trigonometric function or so, that can of course be done easier by just using the usual expansion theorems for these results. So, for example, if f is exponential, then you have just e to the a minus 1 over a, and that is of course a nice smooth function. So that's often easier than Taylor expansion, right?
Yes, but the reason why we went towards Taylor expansion is that the assumption of the code I was working on is that the vector field was polynomial. So yeah. and finding Taylor expansions of polynomials in which you have everything already stored is easier than having a case-by-case approach.
Of course, for polynomials is of course it's the same, right? So, but if you include other nonlinearities, then it might be easier to do that directly.
Yeah, then the problem would be more like practical on the fact that my code would not be running on another nonlinearities.
Yeah. So, okay, I mean it mathematically, not code-wise.
Yeah, mathematically, yes, definitely. There are definitely better, depending on the problem, there are definitely better ways than always doing Taylor.
Yeah, thanks.
Thank you.
Other questions, comments?
Well, I actually have another remark if nobody else is coming. So this change from going from the original coordinate system to the new coordinates where a is involved, I think one can nicely interpret that as a change of coordinates. So you have before you have lambda as an input parameter, right? So which you give into the system, and then you see what happens. And when introducing that a, you make this a new input parameter, and lambda is then a part of the solution. So it's, so to say, an output parameter of the problem. I think in that interpretation, it is, at least in my head, it's easier to understand what is going on here. So actually, finally, you have a curve, or you have a solution x depending on A and lambda depending on A, right?
Yeah, I had never thought of it that way, yes. And that would solve the mental gymnastic that I do by having the fact that now I have two values of A for every value of lambda, but if you indeed shift it around, then you don't have this double problem anymore.
Yes. And of course, then when you so to say, you extend the number of variables of the system by one, namely by lambda, and making A the new, by A, and so the new output parameter is lambda, and in turn you add a new equation, which is the continuation equation. So you add a dimension 1 on the solution side and on the range side. Right? So the lambda is the new part of the solution. So the solution is extended by dimension 1, and also the system is extended by dimension 1 via the continuation equation. This, yes. At least that's my way how I like to see that.
Yes. That's a nice explanation. Yes, thank you.
So actually I have a question. So right now you're applying that to a 1D PDE. So do you think it's reasonable to start thinking of applying these techniques to two-dimensional PDEs, or it's still like at the frontier of computational limitations right now? So how accessible are higher dimensional PDEs as of now?
So this computation now is taking a significant part of my computer power at the moment. And I just changed computer, and I can finally run these computations without completely crashing the computer. So I think it would be possible, but at the moment here we are talking about 5 modes in time and 20 in space, and that is the absolute minimum to make the validation work. If you were to increase the number of modes, increase the number of dimensions, so you're going from like 20 modes in space to 20 times 20 in space, I honestly don't know if a single computer could handle it. On the other hand, it's mainly like the bottleneck is the storage of the operators involved in computing the Z1 bound, because they are you have in the Z1 bound you have A dagger minus df all multiplied by pre-multiplied by A. So that is the only point in which you're juggling 3 operators that are each big. And because D of f has that like band structure, so we go from this and then we state that it can be approximated with this other thing, but at times we need the full operator. And the one time in which we actually need it is the moment in which the computations are heaviest. So I don't think it would be possible on a laptop to handle it, to go to two-dimensional PDEs. It's not like mathematically there is any problem. It's really just that you have to store all the information somewhere. Mm-hmm. I assume that someone better than me at coding could handle the code in such a way that doesn't need to keep so much information. Yamawa at some point proposed to have a way of just computing line by line and column by column the operator, so you don't need to store it at one time. That would solve the problem. Mm-hmm. So I think my answer is it would be possible, but not for me.
Maybe one could also add that mathematically, as you said in a so to say, as a side remark, I would put more emphasis on that mathematically, this is no problem, right? So yeah. The concept of introducing the A, this regularization techniques and everything works on a very general level.
Yes.
It is only in quotation marks a computational problem to go to higher dimensional problems.
Yes.
But not mathematically. Of course, that only is, of course, it's still a big problem, but it is a problem which may be solved in 10 years.
Yeah. As I was saying, I went from an older laptop to a newer laptop, and that was enough to actually run this computation smoothly. So we just have to wait long enough.
All right, let's be patient then. All right, other questions, comments?
I would like to have a question.
Yes, Akitoshi.
Yeah, I'd like to figure out your main motivation of this project. So if I understand correctly, so you can directly determine the Hopf bifurcation point by using a zero finding program. But you use the, I mean, maybe kind of some continuation notation. Then you continuate the saddle node bifurcation, and then you can find the some Hopf bifurcation point. Why you don't directly find the Hopf bifurcation point?
I mean, setting up the Hopf bifurcation point as actually finding the imaginary eigenvalues of the f in the ODE system is possible. I have code that does it.
Yeah.
But I was most interested in validating the periodic orbit around it. So when, let me go all the way back to here. Finding where the Hopf bifurcation is happening can, in ODE systems, it's possible to do that. And it's just transforming your dynamical system into an algebraic system. But then you have only normal form information about how the periodic orbit is coming off your fixed point branch.
Mm-hmm. Mm-hmm.
And that was
so you don't you can find not only the bifurcation point, but also whole, I mean, the neighborhood of bifurcation point.
Yes.
Yes. Okay. Yeah, I understand. Yeah.
Yes.
It's very nice. It's very nice approach, I think. Thank you.
Thank you.
Yeah, so a motivation, at least that I have, because I was involved in the ODE part of this, is so if you have, so I have a project with Jay and Carlos and Renato, and then we want to continue to actually go from at the onset of bifurcations. We want to do a continuation of periodic orbits in the celestial mechanic problem, in the n-body problem, and there was a conjecture. I mean, in fact, Renato Calleja talked about that some weeks ago, about Marshall's conjecture, that we call it. You know, that there are some bifurcations from the polygonal central configuration through, axial bifurcation that connects all the way to the figure 8. And that requires really going from the bifurcation. So basically doing a continuation from a bifurcation and continuing all the way to another one. And that requires kind of desingularizing bifurcations. And the most difficult bifurcation in that case is from the polygonal to the spatial families. And that a similar trick here, very similar to the one that Elena talked about, like desingularizing and introducing this amplitude parameter, really seems to kind of be the key idea. So that's kind of, I think, kind of when you want to do like rigorous branches, but all the way through a bifurcation. So these kind of ideas are helpful. In fact, I think that Kevin Church, who just spoke before, I think he has also a project in impulsive delete differential equation. And the goal there was also to do a continuation of periodic orbits at the onset, from the onset of Hopf bifurcation. And he used a similar trick as well. So it depends on the problem.
I'm interested in this. Is very general setting.
Absolutely.
Yeah, it's very nice.
And in fact, when we started to work on that, and I first proposed to Elena to just look at the algebraic, because it's kind of very straightforward to set up a zero finding problem to pinpoint exactly where the Hopf, but you don't really have an information of the family. And JB was more ambitious, and he's the one who pushed for, I mean, to really get us to prove that you can kind of remove the branch of steady states, and then you really see that you have in the remaining system you have a saddle node of periodic orbits from which you can do the continuation, and that's much more general and constructive because you can really go through. I mean, you can desingularize and then kind of really get from the onset you can compute things. So yeah, I think it's a nice setup.
Yeah.
Okay, other comments or questions? Okay, well, if not, it's exactly 11, so perfect timing. Thank you very much, Elena, again for your nice talk.